Hello everyone, welcome back to another video for the series. And I think I mentioned yesterday that I will be solving a problem related to Dazer's theorem like today. However, I noticed that problems that are related to Dazer's theorem is either too easy or too hard. So I had really hard time choosing a problem, and like most of the problems I couldn't even understand. So that's why I just decided to do um, an easy number theory problem that I made today. And then tomorrow I might come back with a problem related to Dazer's theorem. So today, because I think I mentioned that I will be uploading more videos on number theory. So today I think it's like the succeeding video from the last one where I did really rudimentary one, that is Euclidean algorithm, and this one is also like quite like basic, not basic but not too advanced theorem. It's called Chinese remainder theorem. I currently don't have like a rigorous and formal definition of the theorem. However, but I know the theorem, so I think I can explain the way I understood this theorem. Because I feel like if I just memorize the theorem and like trying to copy and paste it, it's not really like understanding the theorem. So this is how I understand it. No, actually it's the same theorem, but I just rephrase it quite a bit. So, uh, and also whenever I state the theorem, it might be different. The wordings might be different because I didn't like really memorize them, but I just know like what it's saying. So, I will say consider the following congruences where a equals a sub 1 times a sub 2 times a sub 3 dot 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 a sub k, and n equals, no, I will change to such that 2 dot 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 n sub k, where a sub I, n sub I are integers, and n sub I comma n sub j equals 1, where we have x is congruent to a sub 1 mod n sub 1, a sub 2 mod n sub 2, all the way up to x is congruent to a sub k mod n sub k. Then there exists a unique solution to x is congruent to a wait. Oh, no, actually, never mind. It's not true. Such that a mod n. This a is just anything. It's not related to a sub 1. I mean, it's somewhat related, but not like, yeah. So then, why am I keep writing it wrong? Then there exists a unique solution to, okay, so this is like basically what the theorem is saying. Consider the following congruences such that and yeah, so this means they are pairwise. I'm not sure if this is mathematically correct, but I just wanted to say that n sub 1 through n sub k, they are pairwise co-prime to each other. And then there exists a unique solution to x is congruent to a mod n. So let's use this theorem to solve our congruences right here. So I will copy the question here again. I think that's easier. Okay, so we know that 2 times, or we know that I will just write it like this. Or we can do the least common multiple of 2, 3, and 5. No, sorry. We know that 2 and 3, they're relatively prime to each other. 3 and 5, they're relatively prime to each other, and these relatively prime to each other. I didn't write it like this because I heard that this is not mathematically correct, so I have to expand it. Now we know that 2 times 3 times 5 equals 30. So we know that n sub 1, n sub I and n sub j are co-prime to each other. We just know that. And we know that a sub I and n sub I are integers. And that means there exists a unique solution to x is congruent to a mod 30. And we're going to find this a. And that's like really simple from here. And you might also ask like, okay, alright, sorry, let's change this first. You might ask, like, why is this considered like an Olympiad problem? And like I mentioned in the previous video, if you're curious, you can check out the video, my reasoning behind that. Thank you. Okay, so we have mod 5. I hope this is right. Because I made this problem and I couldn't like really fact check it. If I get it wrong, please notify us in the comment below. Okay, so using our first congruence, we can write that x equals 2k plus 1, where k is an integer. Then let's use this to substitute it right here. Plus 1 congruent to 2 mod 3. So I mean it's just like, so you have 2 mod 3 because, and 3 equals 1. Wait, yeah. Therefore, k equals 3k prime plus 2. So we know that x equals 2 times 3k prime plus 2 plus 1 is 6k prime plus 5. Okay, now we didn't use this one yet, so we have 6k prime, 5 equals 2 mod 5. K prime equals negative 3 mod 5. 2, 10, so we have 2 mod 5. And that is because 6 and 5 are relatively prime to each other. Now, we know that k prime is equal to 5k double prime plus 2. So let's resubstitute it. We know that k equals 15k double prime plus 8. So therefore, x is equal to 30k double prime plus 17. Then we know that x is congruent to 17 mod 30. And we solved our the congruences. And the reason why there's no error here is because we by Chinese remainder theorem, we know that this is the unique solution. And also we use our first condition, we also like here, and we also use the second condition to to like narrow down our x values. And then we also use our third one, so we use everything. And if you want to fact check it, we know that x is equal to 30a plus, not a, because we have 30 x prime plus 17. Let's substitute it here. We yeah, so if we substitute it right here, we know that so we know that this thing is true because by our condition. And second one, it's also congruent to 0 mod 3, which is already also true, and it's equal congruent to 5 mod 5, 0 mod 5, which is always true because like 30 is divisible by 2, 3, and 5. Therefore, we also checked it again, and indeed our solution is correct, I think. If you think I made a mistake, or if you think you have a better solution, please feel free to share that in the comment below. And tomorrow I will come back with another problem, maybe the one that is related to the Dazer's theorem, hopefully. And I hope you enjoyed it, and thank you, and see you tomorrow. Bye.